This semester, we've used traces to figure out what the graph of quadric surfaces look like. We're going to use that same idea to figure out what graphs of multivariable functions look like. We're going to pick traces specifically parallel to the xy plane, so traces like z equals 1, z equals 7, z equals -5. We'll use each of these traces stacked together to figure out what our function might look like. For example, if we're looking at the function g of xy, defined by the square root of 9 minus x squared minus y squared, we might pick to create a trace in the z equals 0 plane. Now remember, z is our dependent variable, so we could even write that that expression is equal to z, which would make it easier for us to see that we're going to take the function definition and set it equal to 0, the plane that we're using to create the trace. Setting this equal to 0 will allow us to square both sides of our function, to get rid of the square root on the left. Still 0 on the right. And now we're going to rework this equation until it's more familiar to us. We see the equation 9 equals x squared plus y squared, and hopefully we recognize that as a circle centered at the origin with radius 3. We can repeat this process for any plane parallel to the xy plane. So maybe we try another one at z equals 1. That would mean take the definition of our function and set that equal to 1, and simplify until we recognize what the equation graph would look like. In this case, the trace in the plane z equals 1 produces the equation 8 equals x squared plus y squared. Now that's definitely a circle centered at the origin. The radius is not as nice as the radius in the z equals 0 plane. We need to find a number that when we square it, it's equal to 8. The best we can do is the square root of 8. So our radius is square root of 8. And if we were to check that on a calculator, we could see that the square root of 8 is just a little bit smaller than 3. So if we wanted to create a graph of these traces, we can start by creating our 3D axes. And then we can sketch each one of these curves. In the z equals 0 plane, we found a circle centered at the origin with radius 3. Then we shifted up and we moved into the z equals 1 plane. And in this case, we found a circle centered at the origin with a radius of root 8, which we discussed was slightly smaller than slightly smaller than 3. So if I were to pick this to be z equals 1, I'm basically going to draw another circle that's just slightly smaller than the blue one. And we can repeat this process. So if I were to move up to z equals 2, I'm going to notice that I get another circle with an even smaller radius. And then when I move all the way up to z equals 3, if you remember, we found that we were at the top of the dome, like a point. Now this is a really rough sketch, and if we were to kind of picture it from the side, it might be easier to visualize that we're looking at a bunch of stacked circles. And if you remember this function from the previous video, it was the top half of a dome. And that's exactly what we're starting to sketch up with each of these traces. Let's try another one. We have h of xy, and that's defined by x squared plus y squared. So we're going to create a few of our traces by picking some plane parallel to the xy plane. We could pick z equals 0. That would give us 0 equals x squared plus y squared. The only x and y combination that satisfies this is a point. So we know that when z is equal to 0, we are at the point 0, 0, 0. If we shift up to maybe z equals 1, we would set our function equal to 1. And here we can see that we're at a unit circle. So at z equals 1, we have a circle with radius 1 centered at the origin. Moving up to z equals 2, we would have 2 is equal to x squared plus y squared. That's another circle centered at the origin, this time with a radius equal to root 2. So we're going to shift up on our graph to z equals 2. Root 2 is larger than 1, so this circle is going to be larger than the previous one. And maybe we're starting to recognize the shape of this surface as a paraboloid. So we started off with a point, circle, 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 and they're just going to get bigger and bigger, mapping out our paraboloid. So we can use these traces to help us figure out what a surface looks like, even if it's not a quadric function.